Hi everyone. My name is Shobhi Jain, and I'm working as a software engineer in Intel Corporation. And today I have Timothy Miskell, one of my colleague, who has joined us virtually. Maybe Tim, do you want to say a quick hello to everyone?
Yep, hey everybody. Hopefully everybody can hear me. This is Tim Miskell from Intel, software architect here.
Yeah, so today we will be presenting on the topic that is deep dive into the protocol agnostic filter technology on Ethernet adapter with DPDK. I know it's a long title, but the core of this talk will be around, we will be basically talking about the protocol agnostic filter technology. And again, I know it will be the third time in a row that you will be hearing about the generic flow, especially the RT flow. But in our presentation, we will be mainly concentrating on the raw pattern within the generic flow. So maybe we will start. So we have a kind of full agenda. So we will be talking about the problem statement, and in the problem statement, it will be mainly what Lucas has already talked in his presentation. So I think so we should have collaborated for our presentation, Lucas. So we will be talking about the problems we faced when we talk about the Ethernet adapter, and then some of the possible solution. And one of the possible solution is what Lucas has already talked again, that is SmartNICs. And on top of that, we have again one more approach, that is the raw pattern, which we can configure on top of RT flows that we will be talking about in details. And also, we will be going through the Arista L2 timestamp as a use case in order to explain how someone can configure this whole raw pattern. So, talking about the problem statements. So, if we see things from the Ethernet adapter perspective, what are the main problems which we see? First of all is the reduced system performance. So like in high performance networking environment, when we talk about telecom data centers, like high throughput and the low latency, I think so we all are from here, the like networking background, and apologies if it is something you all already familiar with, but just wanted to bring everyone on the same page, so that's why I'm talking about these problem statements. So yeah, high throughput and low latency, this is the bread and butter for all the network software engineers. But when we talk about, when we see things from the like a network adapter perspective, and especially from the flow classification perspective, so like if there is no proper mechanism in place for the flow classification, it actually affects the overall performance of your system. Next is system flexibility. So like different applications requires like different classification flows, and also like they need like different type of traffic that needs to be classified. So if we don't have an efficient mechanism in place, it can be really slow and complex, and also like we won't be able, it is not flexible, so we won't be able to actually, we won't be able to classify larger number of packets or like different type of packets. And complex and slow flow classification. So the point which I was saying just now, that like if there is no proper mechanism, a flow classification mechanism there, so in that case the classification can be slow and complex. And the next problem is difficulty in hardware offloading and integration. So like if there is like if the hardware doesn't support proper flow classification mechanism, then the software won't be able to offload those flows on the hardware. And the last is inefficient packet processing. Obviously, this if your hardware doesn't support processing of the packets or processing of the flows, then you have to do everything on the CPU, and it will actually affect your line rate. So all the problems which we have talked about here now, there is one solution for that. That is the programmable NIC with programmable packet processing pipeline, which Lucas have already talked about a lot. Few examples are here. It's like Intel Ethernet adapters, which is like 700 series, which we call as like Fortville, and also like 800 series, which we call as Columbiaville. Also like Tofino switch, so the switch which has P4 programmable switch, and also NVIDIA Connect 6 and Connect 7, and also like Cisco Silicon. And there is a long list of the Ethernet adapters who actually provides programmable like a packet processing pipeline. So these packet processing pipelines actually offers significant advantage in terms of flexibility, performance, and customization. But their biggest challenge is in the complexity in programming and development of the driver. So because now driver has to actually support the parser capability for all of them. And that's where actually the protocol agnostic flow offloading method, named as a generic flow also, becomes helpful. So what happens, the generic flow enabled driver actually learns the network adapter's hardware at runtime and translates the flow offloading request to the specific hardware configure commands. And this learning mechanism actually keep the driver unchanged even though the hardware has been reconfigured. So if we take an example of like Intel Columbiaville, like that is Intel Ethernet 800 series. So like that particular adapter, Ethernet adapter, with the help of its like dynamic device personalization profile, which we call as a DDP, which is very specific to like this particular Ethernet adapter, but like it can be like if any other adapter which has something similar capabilities can also actually support configuration of the generic flow. So again, like the advantage of the generic flow methods, Lucas and Adam have already in their presentation covered a few of these things. So I won't be going much in the detail, just like a quick. So now the efficient packet processing, because now you are not like, now you can offload your like flows on the hardware, and so you can so your line rates, so you have a better line rate here, and more flexibility, because now like as new protocols are developed, like a protocol agnostic system can handle them without hardware or driver upgrade. Improved system performance, so it is linked to my point above, that is it removes the requirement for CPU cores on the host to perform the classification and the load balancing of the packets. So it helps in increasing the packet throughput and reduce the packet latency. And also the deep packet visibility, because generic flow can help inspecting and acting on the inner headers or the payload, and enables advanced use case like deep packet inspection, QoS, and the security filtering. And the last one is the ease in hardware offloading and the integration. So now hardware can actually offload those easily, and also like there is no hardware specific limitation here. Going a little bit into the how this generic flow offloading is being, so in the DPDK, in the DPDK, this generic flow offloading is being enabled by RTE flow. And this slide, I think the content of this slide, you might already be familiar, because again, Adam already covered that what are the few of the functions in the RTFlow API, which helps us enable this functionality. So like if application, when an application wants to create a flow, so the RTFlow create functions get called. It actually then defined some of the components, theirs, and their attributes, pattern, and actions. Then once the flow creation has been done, then the RTFlow validate happens, that next checks that if it actually supports that particular flow creation rules or not, and if it is, then the rule gets installed in the NIC. It's again, so like what happens, that RTFlow has a set of predefined data structure, which represent the protocol headers with the field that follows, that mainly follows the industry specs. From a driver's perspective, it is supposed to provide a parser to translate the RTFlow format protocol combination into the hardware configuration. So like this is how from RTFlow side of things works, that there will be a, like the packet will arrive with a certain protocol combination. Then the flow table will be checked for that if there is any associated pattern there in the flow table which matches with the packet. So it's kind of like it checks whether the attributes, whether it's an ingress traffic, egress traffic, and what's the priority of the traffic. Then it goes in the pattern items to check, match the items. If the pattern item match, it performs the associated actions, and it can be any actions like drop or send the traffic to the certain queue. If not, then it performs the default action, and the default action could be that drop the packet or send it into the particular queue so that it can be inspected further. But here, like I said, like RTFlow has a set of predefined data structure. But what if we want to support a new protocol that actually like have a new data structure? In that case, there will we need a new data structure in the RTFlow. And since the driver parser cover the limited cases, then the new parser logic would be needed to be added to support the new packet types, even if the protocol exists. And that's where actually the protocol agnostic offloading helps. So it is a DPDK feature which actually so in RTFlow there is a raw pattern type which you can use in order to actually enable that. So how the raw pattern type works in the RTFlow. So again, the flow remains same. If you see, there is only a new block added, that is a raw pattern match. So in this case, when I say raw pattern match, is like if suppose user wants to do a flow classification on the basis of any like arbitrary value. So I will be explaining in the next slide with an Arista like a use case where they wanted to hash on the basis of the timestamps value. And in that case, that is where their raw pattern actually helped them. So in that case, they didn't need to like rewrite the whole driver in order to support that particular flow or that particular pattern. They just used the raw pattern, and they were actually able to hash on the value of that. So how the flow now looks like? So now the pattern arrive. Now if you see the difference from the previous slides to here, so now the only thing is now here the raw pattern is used instead of the pattern. And in the raw pattern, there are two things which we mainly consider is the spec and the mask. In the specs, it's like the value to match, and the mask are the offsets or the value on which the user wants to actually do the like hashing. So packet arrives, again same things happens. It will check if there is any like a associated flow. So it will check for any ingress, like what's attributes, then it will go for the exact match pattern. If it doesn't find any exact match pattern, then it will check that if there is any associated raw pattern matches there, and in there it actually will check for the spec. And last is also kind of an attribute. It's like an upper bound for an inclusive range with corresponding field in spec. And mask is the bit mask applied to both spec and last, and the purpose of this mask is to distinguish the values that should be taken into the account, or we can partially mask them out. So yeah, so then it will if that there is no raw pattern match happens, then it will perform the default action. If it does, then it perform the associated action. So now moving on to the so sometimes it is difficult to understand that, okay, how this whole thing is working. So we thought of taking this an example, explaining it with an example, and that is the Arista L2 timestamp. Like I said, in the Arista use case, what they wanted to hash on the basis of the timestamp value. And so this is kind of a packet, like a format which they had. And if you see in here, basically, like there are some color coding happening here. So we have source in the blue. It is the source MAC address. In the destination, it is in the green. It is the destination MAC address. And there are some specific bit on which Arista wanted to pass on as the as a part of the specs. So if I see that how the spec and mask in this case are going to look like, so if you see, we have first destination IP address, again we pass it as it is, and then we have source IP address, then we have vendor specific protocol, and then we have timestamp, and these are something specific to this particular use case. And then we have the changing L2 timestamps value. And because we wanted to hash on the basis of these changing L2 timestamp value, so our mask were we actually masked those L2 timestamps value. And like I said, this is very specific to Arista case, but using the same methodology, we can actually calculate the specs and the mask for any other use case also, and we can just pass it into the raw pattern when we are configuring our flows, and we will be able to achieve we will be able to classify our flows on the basis of that. And whenever we talk to the different customer, when they use this raw pattern mask, or maybe when they are calculating this spec and mask, they always get overwhelmed that how this specs and mask can get calculated, because sometimes it is tricky to calculate these specs and mask. And for that we actually have, first of all, before I go into that particular tool, so this is how your test PMD command is going to look like. So if you see, what Adam and Lucas just shared, that in their example, it was mainly flow create 0 ingress pattern, and then it was the what are the pattern they want to match on. But in this case, it is just in this case we actually now have raw pattern, and then it is followed by the spec and the mask which we actually calculated above. So this is now how your command is going to look like in the test PMD side. And the thing which I was mentioning, that sometimes a user gets overwhelmed about how to calculate this spec and mask for their particular use case. And in that case, there is a tool which is available called as Packet Forge. It is open source. So in that case, you can just provide your rule, and it will actually helps to calculate your specs and mask. So if you are needing some help that okay, how to calculate this, you can use this. I've actually included the link of that in the slides, so if anyone is looking to use that particular tool, they can. And also, this whole presentation is actually based on the white paper which we have initially recently released in collaboration with the Arista. So if any one of you is looking for more information around that, okay, like why Arista was doing the time, like hashing on the basis of the L2 timestamps, or if you want to, if you are looking for more information on any of these functions, that okay, how RT flow create or how RT flow API is working. So it is actually there in the, so I've included that link of that white paper also in this at the end of the presentation. So feel free to check it out. So you will get more information around any of the topic here. So yep, so these are the references. Like I said, it has like packet forge link. It also has the link of the like the white paper, which I was just talking about, and also it has the like a DPDK. I think so. Yeah, it is one like one more document which can which also have like can help a user to like having more understanding around the specs and mask and how the whole raw pattern is being calculated. This is a like second paper which can help you guys. So, yep. So that's all from my presentation actually. So, like if you have any question, please let me know.
Is the code public?
Sorry?
Is the code, I mean, is it in the, it's that
Yeah, so...
RT flow, sorry. Sound right? Okay. Is the RT flow, generic RT flow action, sorry, match and action, is code available now?
Yeah, so it's like it's in the DPDK. So in the like I said, like it is in the DPDK. So there is one particular in the DPDK raw pattern, like that particular feature. So when you are like setting your flows or configuring your flows,
Okay,
you can use that. Yeah,
the source code is available.
Yeah, it is available.
And this tool to JSON file, so that's also not available as well.
Yeah, it is available. It's open source. It's
so
available.
How deep we can go in the packet?
Sorry?
How deep?
How deep that particular tool can go into the packet, or like...
No, I mean mask. I mean the mask length.
Mask length. I don't remember straightforward. Tim, do you remember like how deep up to how deep we can go into the packet actually?
So that depends upon the particular parser and the particular NIC you're working with. But I will say it's more in the order of, say, hundreds of bytes typically, rather than thousands of bytes. So it just depends upon which particular adapter you're landing on.
And then how about number of rules you can scale?
So I think so number of rule, it will depend upon your like how much your hardware can support.
That's true too. I mean, as a general rule, say for the 800 series NICs, it's on the scale of, say, thousands of rules. But again, it depends upon the particular adapter you're landing on. So, and the complexity of the rules too.
Hi, Shobhi. Thank you. Lucas here. I wanted to ask, but I think you answered it with the previous question, if it's supported on regular E810 NICs. That's great. When I was evaluating the pattern matching for Suricata, and I also basically looked at the raw action in RT flow as a, let's say, inline pattern matching opportunity there. It almost fitted my requirements. It just didn't support the case insensitivity, which, I mean, this whole idea about the raw pattern wasn't probably developed with the idea of pattern matching, but I think it could be a side use case as well. Does the current support also of the row pattern the other subfields like the offsets and depth that are kind of specified in the documentation?
In the white paper?
No, in the implementation. Does the implementation support because the spec what you had also allows to specify how deep the pattern should be located, or at which offset it should start searching for the pattern or for the bytes. So I was just wondering if it's already also supported in the current Intel implementation.
I think so. I can check for you and come back to you with that. Tim, do you know about this actually?
Well, let's say if I kind of understand the question correctly, if you're talking about things like VLAN headers and so forth, if you are configuring the NIC to strip those things out, certainly that would help in this case. You don't have to worry about the offsets in particular. Other things like MPLS labels can also be accounted for. But I mean, if there's anything particular that does require a particular offset, like Shobhi mentioned, we can follow up there.
Okay. And is there any chance that the current implementation will support the byte matching on whole packets and not just the first 100 bytes?
I think so. In that case, you can mask them out, whatever you are looking to match on. So you can actually mask them out with the help of the mask.
Yeah, but I think you still mentioned that the search only goes for the first 100 bytes, or maybe Tim mentioned that
yeah,
it's in the order of 100 bytes and not in order of thousands. So packets can be 1,500 bytes long in general. So I would kind of like to match on the whole packet. So I was wondering if this can be supported in hardware.
I think so. Like Tim said, currently only the 100 byte is it can go up to the 100 byte, but yeah, it won't be like you said. You want to match if you want to match the whole packet, then in that case you need to select a certain bit with up to the 100 bytes only. Yeah.
Yeah, I was going to add there. I mean, we're still limited by the parser itself. Yes, I mean, whatever that restriction is on how many fields we can go into the packet. I mean, in general, we're not going to be able to get to say like the HTTP layer right of the packet. We're still going to be bound there by the hardware.
And also,
Sorry, can he use the mic?
no, I'm just thinking about it slightly differently here. Like, I don't know, there are solutions we developed where we have a chain of mask or matching rules. And then each action is also a matching for the next, so it's a chain of things. And the back end, we do not have a hardware, we have a software implementation, right? Which is very simple, like drop a packet or, do something else, right? But the whole thing is all about the hash lookup of all this chain of matching of different masks, different offsets, right? So do you support this chain of rules, rule match and actions?
I think so. Yes, Tim?
I was going to say we can follow up there again. But I mean, there are still some limitations there, but I mean, you can certainly, chain certain combinations together.
Yeah.
Hi. Do you support the flow for VFs on the 810 NIC as well, or is it only on the PF?
I think so. It's supported on both VF and PF. Am I right, Tim? Sorry, because Tim is like a technical lead for this, so I.
Correct, Shobhi. Yeah, it's both the IVF driver, the VF, and the PF in this case.
It is supported.
Yeah, on so IAVF and on the PF side as well. So.
Okay. Because the last time I tried on a 5.15 kernel, the ICE driver didn't have support for it. Maybe it's added recently, or.
Yeah. maybe you can give it a try. If you have any problem, reach out. Maybe we will be able to help.
I already had a problem, that's why I was asking. Thanks.
Okay, I think we can close. Thank you.
Yeah, thank you so much, everyone.